Hello students, today we will be starting a new module and in that the first lecture will be urban ecosystem and the linkage with CO2 and methane. So if we remember what we have discussed in the last 3 weeks, first week we have discussed the ecosystem basics, second week ecosystem types and theories, and third one week we have discussed different aspects of ecosystem like components, different aspects of urban ecosystem like urban ecosystem components, their functions and processes, urban metabolism. We discussed in detail urban ecosystem and water, and also we discussed some interesting demonstration projects of urban ecosystem and water. So that's the way we concluded the third week. Fourth module will be working on the urban ecosystem process. As we have already understood the basics of natural ecosystem and the urban ecosystem, it is good to see which are the important processes and important elements which influences this urban ecosystem most. Two most important elements which are influencing the urban ecosystem are the carbon dioxide and the methane gas. And we will discuss them under the broader umbrella of greenhouse gas emission. So, in this particular class, we will be looking at the carbon cycle in the urban areas, carbon imbalance, urban climate dome, and emissions. Also, we will look at the solution side. So, we will look at the urban climate sink, and lastly, we will discuss briefly on the methane in the urban ecosystem. As we know, these greenhouse gases create an effect which is a natural process, and the gases like carbon dioxide, they trap heat, and this is very important for the earth. Otherwise, during the night time, all the heat throughout the day what earth has received, that will go back beyond the atmosphere. So, to keep the earth habitable, greenhouse effect is very important. But in today's time, we are really discussing greenhouse effect as a negative one. Why so? Because anthropogenic activities have brought this greenhouse gas presence in the atmosphere to a level which is not healthy anymore. And carbon dioxide is the primary driver of this anthropogenic climate change, which is happening due to this greenhouse gas elements presence. Carbon dioxide, as we said, you can see in the US in 2022 report is saying almost 80% emission is coming from the carbon dioxide in the GHG. Methane is the second most important anthropogenic GHG. Another important greenhouse gas is the nitrous oxide. You can see their share in this chart. Fluorinated gases are also very important to take note of. They are synthetic, powerful greenhouse gases. It's a completely anthropogenic gases. When we talk about carbon dioxide, let us see quickly the chemical properties of the carbon dioxide. A colorless, odorless. So you can't smell it even if it is present in around you. One carbon and two oxygen atoms create a CO2 molecule. It's a three atom structure which allows it to vibrate and absorb infrared radiation, that is the heat, and which it then re-emits and warming the surface. So initially it absorbs it, then it re-radiates it, and then the surface as a result gets heated. Atmospheric concentration. Pre-industrial level, which we always take as a benchmark, is around 280 parts per million, ppm we say. But 2023, the global average has reached 419 ppm, a 49% increase. And this rise is due to fossil fuel combustion, industrial processes like cement production, steel production, and also deforestation and other anthropogenic activities. Carbon cycle, let us look at its reservoirs and the time scales. The global carbon cycle is a continuous exchange of carbon among the atmosphere, oceans, land, and lithospheres. So, the biosphere, atmosphere, lithosphere, they are continuously exchanging hydrosphere, they are continuously exchanging this carbon. We generally find two types of carbon cycle. One is slow one, the other one is first one. Slow carbon cycle, movement of carbon through rocks and sediment over millions of years. That's a very slow process. Most of Earth's carbon is stored in these rocks. So, in today's time, through mining, we are bringing it out. Otherwise, nature has made a very safe store for them. Slow cycle actually acts as a natural thermostat for the planet over geological time. First carbon cycle, rapid exchange between the atmosphere, oceans, and biospheres. It can be day to millennia. Photosynthesis is the largest flux, absorbing 125 petagrams of carbon, equal to 10 to the power 15 grams of carbon annually, far exceeding fossil fuel emissions. So, if we give a chance for this photosynthesis in our urban areas, probably most of the aspects of today's problem, including pollution, can be curbed significantly. We have to remember oceans are critical net sink, absorbing a large portion of anthropogenic carbon. So, in our discussion, again and again, this marine sink will come in the picture. The carbon cycle has received particular attention because 60% of the observed global warming is attributable to the increase of CO2 concentration from about, as I discussed, 280 micromole per mole of dry air in the pre-industrial period to today's 419 micromole per mole of dry air. So, as we were discussing that we will be discussing these reservoirs, let us see which are the main reservoir for the carbon. Atmosphere, biosphere like plants, soils, hydrosphere, oceans, and lithosphere like rocks and sediments. Key processes involved, definitely photosynthesis, respiration, decomposition. You remember we discussed the upwell, that is that ocean uptake. Volcanic and weathering cycles are the important processes for the carbon cycle. Nature always believes in balance, so carbon fluxes are cyclic and relatively self-regulating over geological timescales, but only till pre-industrial period. Let us see this carbon cycle once again. If you remember, in our first or second week, we discussed this carbon cycle, which is a biogeochemical cycle. So, it is having the biotic components, it's having the geological references and chemical processes. Main reservoirs, already we discussed, it can be the ocean, it can be the any other river, lakes, ponds, it is that mountains, soils, the plants are there. So, there are lots of things which are the reservoir, which acts as reservoir for carbon. Key processes, just now we have discussed photosynthesis to decomposition. We will look at them once again. In this biogeochemical cycle, we can see the very strong role of ocean, which is serving as a major carbon sink, absorb atmospheric carbon dioxide that is far greater than that of the atmosphere itself. So, it plays a fundamental role in regulating the global climate. The oceanic carbon cycle mediates carbon exchanges between the oceans, atmosphere, earth, and seafloor, and significantly regulates the atmospheric carbon dioxide levels, impacting the climate and ecosystem. So, if we have to really resolve the problem on the terrestrial ecosystem, we need to look at the ocean as well. Terrestrial and aquatic plants and algae, they are very important because they actually can intervene with the oxygen cycles through photosynthesis and intersect with the nitrogen and phosphorus cycles. And collectively, they bring the overall carbon dynamics in place. Climate changes and significant environmental shifts, such as extensive ice melting, temperature fluctuations, they impact global carbon cycle critically. So now let us see the carbon cycle in the urban ecosystem. We are having the new carbon reservoirs in the urban ecosystem. Built environment, concrete, asphalts, plastics, infrastructure, then urban soils and human biomass. They are the new carbon reservoir. Altered fluxes, huge inflows of fossil fuel derived carbon for energy and materials come from many different places to the urban areas. Limited carbon uptake due to reduced vegetation cover. And very interestingly, the artificial respiration through the vehicles, industries like plumes are coming out, HVAC system, carbon is getting added to the urban ecosystem. Unlike natural ecosystem, which tend towards a carbon balance, urban ecosystems are overwhelmingly net sources of carbon emissions. If you remember, we discussed this particular point in our previous week. Like pollution is one of the most important ecosystem process which is intensified by industrial activities, human and vehicular traffic emission. We also discussed about the carbon sinks there. Here we will be discussing carbon imbalance, carbon dome formation, its health impact, energy penalty, and we will discuss the emission sources, building, transportation, industry, which are very common in the urban ecosystem. Urban carbon imbalance. Urban metabolism is linear and open loop, breaking natural cycles. Cities import massive quantities of carbon dense resources from the hinterland, and we can call it as horizontal fluxes. And these resources are converted into concentrated emissions of GHG through usage and then released into the atmosphere. So, vertical fluxes are now getting created, and we can see the formation of vertical emission layers due to the built form and heat island. So, not only the fluxes are getting created, it is also layered now. So, the urban system lacks the biological capacity to reabsorb this waste. Urban areas are responsible for over 70% of global fossil fuel related CO2 emission. So, the carbon dome, to give you a very good idea, you can see this particular image on the left hand side, which is showing the representation of this dome idea. Urban carbon dome, or we will be discussing the UHI later on, is a measurable dome of elevated CO2 concentration that forms over cities. So, over the city you can find this dome, and many a times it is so polluted, the cities in certain parts of the world, that you can even see that, sense that. Formation drivers, concentrated sources like high density of traffic, buildings and industry, and also altered meteorology. The UHI effect, where materials like concrete and asphalt trap heat, make cities warmer than the rural areas. And this creates a stable urban boundary layer that traps the pollutants and behave completely different from its rural neighborhood. Magnitude of this carbon dome depends on the CO2 levels in the cities and it can be up to 75% greater than the surrounding rural areas. Let us see the impact of carbon dome on the health. Higher temperatures from the urban heat island accelerate chemical reactions that produce harmful secondary pollutants like ground level ozone and fine particulate matters PM 2.5. And this effect is estimated to cause an additional 300 to 1,000 premature deaths per year in the country of US. So you just imagine in other countries where there is no such measure or monitoring what is happening there. So this suggests reducing local carbon dioxide can have immediate public health co-benefits. Now let us see its impact on the energy side. We can say the energy penalty. Buildings within the high carbon dioxide dome need to increase ventilation to maintain the indoor air quality. And this leads to higher energy use for heating and cooling. In Shanghai only, this has been monitored that it has caused a 20% increase in annual energy loads for buildings on high traffic roads. So you can easily imagine what is happening for these people when they are paying not only in the extra energy bill but also on their health side. Now let us come to another important segment of today's discussion related to carbon dioxide and also methane. GHG you can say, that is emissions, and we would like to see from the sectors of buildings, transportation and industrial activities. We can see at the building sector, the emissions, if we try to see, they are primarily having majority is coming from the indirect emissions, offsite generation of electricity and heat which is being utilized in the buildings. Direct emissions are catering to 24% of the emission, on-site fuel combustion for heating, hot water, etc. Embodied emission, you are using different building materials, non-natural. So manufacturing construction materials like cement, steel also has a footprint, 18%. So that's the way we can see building sector is having a strong contribution, direct, indirect and embodied form. So the building sector is a cornerstone of the urban carbon footprint. The Global Impact Report of 2019 is reporting that responsible for 12 gigaton of CO2 equivalent or 21% total global GHG emissions. That's the building sector. This building sector emission rises to 31% when considering only CO2 emissions. Urban form matters. Wealthier households in sprawling suburbs can have per capita carbon footprints up to 15 times higher than residents in dense urban cores due to larger homes and higher energy usage. So, for that only, it is always being promoted to go for compact high rise buildings. Now, come to the transportation sector, which is a dominant and rapidly growing source of urban greenhouse gas emission, mainly from burning gasoline and diesel. And the report is saying that transportation is responsible for 8.7 gigaton CO2 equivalent, accounting for 23% of global energy related carbon dioxide emissions. Road vehicles contribute 70% of these emissions. Urban centers are the epicenter of these emissions. The travel within cities account for 40% of all global passenger transport CO2 emissions. Key drivers are rising travel demand and urban sprawl, which increases dependence on private vehicles. In the US, transportation is the single largest source of GHG emission, almost one third. Now we come to the other segment, which is another important segment, that is the industry. Industrial activity is a core part of the urban economy and carbon footprint. Direct versus indirect emissions in US has been accounted for 23% from the GHG. However, when you include the indirect emissions from its massive electricity consumption, it goes up to the 30%. And then it becomes the largest emitting sector. So, building, transportation, and industry, all three are actually emitting large amount of GHG gases. Key urban industrial sources are the process and the fluorinated gases. The process like chemical reactions in cement and steel production and many other industrial activities, they release large amount of CO2 directly. Fluorinated gases used as refrigerant are extremely potent greenhouse gases with global warming potentials, thousands of times greater than the carbon dioxide. So, urban areas are the major source of these fluorinated gases. So, we need to be very much worried about not only carbon dioxide but also other gases. Urban carbon sinks we'll be discussing now towards the solution part. Green infrastructure, blue infrastructure, and gray infrastructure. So, first one, the green infrastructure, parks, forests, street trees, green roofs, etc. They act as a carbon sink. How? They sequester the atmospheric carbon dioxide through the photosynthesis. So, this particular sequestration and storage in the plant biomass like trunks, roots, and leaves, and the soil, they are one of the major reason why we always prefer green infrastructure as a carbon sink. And it is not only terrestrial, as I mentioned, it's also the marine plants. They also take very strong role. This is a cost-effective nature-based solution which many co-benefits like cooling, stormwater management, improved well-being, etc. If we try to look at the impact, we can see average storage density is 7.69 kg of carbon per square meter of tree cover. But this sequestration often offsets only a tiny fraction of a city's total emissions. Like in Bangkok, it has been calculated, it has been estimated, and only 0.1% of emission is getting offset. So, we have to understand that need is always there for the emission reduction. For coastal cities, blue infrastructure, mangroves, tidal salt marshes, and seagrass meadows, they represent an exceptionally powerful carbon sink. On a per area basis, mangroves and tidal marshes can sequester carbon 2 to 4 times faster than matured tropical forest. So, mangroves can store up to 5 times more carbon per hectare than the terrestrial forest. So, it is always good to see the opportunity in the coastal areas. The key is in the soil. 50 to 99% of the carbon is stored below ground in deep, waterlogged, anaerobic soils, where decomposition is extremely slow, and thus it can actually create a stable long term carbon reservoir. So, thus the way blue infrastructure is so very significant as an urban carbon sink. The last one I will be discussing as the urban carbon sink, you will be surprised, that's the grey infrastructure. Cities' grey infrastructure, especially of concrete, can act as an unconventional carbon sink through a process called carbonation. What is carbonation? A slow, passive chemical reaction where atmospheric carbon dioxide is absorbed by the concrete, reacting with the calcium hydroxide which is there in the concrete to form a stable calcium carbonate. This effectively mineralizes and permanently locks away this carbon dioxide. The process is a natural reversal of a key step in cement manufacturing. Is it a new information for many of us? Yes. Let us see the rate and scale in this grey infrastructure. The rate is very slow, progressing from the surface to inwards only around 1 per year. Over a structure's life cycle, concrete can reabsorb up to 75% of its initial calcination emissions from its cement content. So that's a great reversal. The process accelerates dramatically when concrete is crushed for recycling at its end of life. In the UK, this passive sink removes 1.5 million tons of carbon dioxide annually. That is 0.4% of the nation's total greenhouse gas emission. So you can see a good opportunity in the grey infrastructure as well. So now we will further discuss towards the solution side, and we have to mention low carbon urban development definitely, because we understood our emission has to be reduced. So mitigating urban greenhouse gases requires an integrated multi-sectoral approach. High impact technology solutions will work, like expanding public transport, integrated waste management, and taking waste as an resource for energy and for other things like water, adoption of electric vehicles. But in today's time, we are also discussing, trying to understand the life cycle of these electric vehicles, and there are some questions. But till now, its adoption is been accepted as a very positive technological solution. As it has been discussed, low carbon urban development shall be a system based, systemic one. Urban form and land use planning have lower marginal potential but a wider scope and crucial enabler for this low carbon urban development. Synergies are the key for success. So, we have discussed primarily the carbon dioxide as the major greenhouse gas. Now, we'll be shifting our discussion towards the methane. Methane's chemical properties: primary component of natural gas, one carbon and four hydrogen atoms. It has a very short atmospheric lifetime, like 10 to 12 years, and it is removed primarily by oxidation. Anthropogenic sources are dominant, and that is important to know because we are discussing urban ecosystem and the methane. Fossil fuels, agriculture, waste management, they are the major sources for this methane in urban areas. Global warming potential is a metric created by the IPCC to compare the climate impacts of different gases relative to carbon dioxide. So, carbon dioxide is considered has a global warming potential of 1. So, that's the benchmark, and we try to understand the potential of other gases. GWP, this potential depends on a gas's radiative efficiency and its atmospheric lifetime. So, 20-year potential and 100-year potential of methane is quite different. You can see that. Methane is 83 times more potent than carbon dioxide in 20-year cycle. In 100 years, it is 30 times more potent than carbon dioxide. So, this is that potential, global warming potential. You can see the atmospheric lifetime, which for CO2 is very, very long, whereas methane is very short. And 20-year and 100-year potential, which we have discussed just recently, just now. Primary sources for the carbon dioxide are the fossil fuel combustion. For the methane is the livestock and the landfills. One of the major sector from which we find the methane emission is the waste sector. And in the waste sector, as we have discussed, the agriculture, that's the major one. But next two are the wastewater treatment and the municipal solid waste landfill. Municipal solid waste landfill is the third largest source of anthropogenic methane in US. And as organic waste decomposes without oxygen, it produces landfill gases, and out of which 50% is methane. Similarly, in the wastewater treatment also, we have seen methane is produced during the anaerobic treatment of sewage sludge. So, understanding the risk is very important, but it has to be also monitored that how critical the scenario is becoming. So, what we can do, we can monitor urban fluxes. We can measure, though they are not visible, we can measure them. And actually, that helps appropriate mitigation as well. So, it has been seen that there are many different ways that measurements are being taken up, but bottom up inventories, which are based on the activity data, is a very good one, but it can significantly underestimate emissions like methane. So, we have to be very cautious that when we are monitoring gases like methane, which are the best way to do that. So, I have brought two different options here. One is eddy covariance flux towers. These are in situ towers that continuously measure the net exchange of gases like carbon dioxide and methane between the city and the atmosphere. And it provides high resolution data on a city's metabolic patterns. And that's the way one can analyze the data and take a decision. The other way, satellite remote sense images, which are available in today's time, they can provide daily global maps of atmospheric gases, and thus they enable monitoring of entire metro regions. Crucial for verifying inventories, these steps are. But they face challenges with the cloud cover and spatial resolution. If it is a finer resolution, you get better information. So, I think today we have discussed a very serious problem for the urban ecosystem. That's the carbon dioxide and the methane. And under that, we discussed the cycle, we discussed carbon imbalance, urban climate dome, emissions, urban climate sink, and the methane in the urban ecosystem. So, these are the references for your ready reference. Thank you.